So the experience yesterday, what would be some ways that you would describe what that was like yesterday?
Maybe for multiple chairs.
Yeah, well, how about, who found that very frustrating? Good, you guys are such good sports. So not a lot of frustration. Who found some parts of that very exciting? Yeah, no, I mean, if you enjoyed some part of that, that's important. Can you say that louder? So Naama had some words yesterday that I think summarized at the end of the day what I thought was a very good take on what our first day was like. And this is our Nova meditation for today. Maybe we'll have another one for tomorrow. But our Nova meditation for today is when there are bugs in the software, you learn better. And at 5 o'clock, that was really nice to hear because there were a lot of bugs in the software. So you guys probably learned really, really good, right? This is something to think about as we're going through our next workshops, that as you're running into issues, if we can resolve them, your understanding can improve. One of the things that I noticed and that I was very excited about, and very proud to see you guys do this, and I was happy to see the software do this, is that with just a couple of pieces, with a couple relationships, with a term, with a stock, with a flow, with a graph, even though I was going at a slower pace, I noticed a lot of people in small groups going a lot faster. So that as soon as you're able to generate data, people were plotting it and graphing it. And as soon as somebody thought about a way to modify or change their data, they were able to do that as well. Some other ideas from yesterday, some other feedback, is that things went really fast sometimes. And it was very good to have people in the group, raise a hand and say, what just happened? Can we take a second and make sure that I got that clear? So today we're going to be a little bit more methodical, a little bit more organized, and we're going to go maybe even a little bit slower than yesterday. And I'm still excited to see you guys, as you're getting more comfortable with Nova, work at your own pace. Because that's really one of the powerful things that a visual platform gives you. If you can learn how to specify one organization or set of relationships, and you can think about how you might extend it, nothing stops you from extending it. You can add another term. You can add another stock, another flow. You can take your XY coordinate position data and start trying to get the distance from the origin if you know how to implement that. I think some people were starting to do things like that. So that's number one, our meditation for the day. For the day, that's our meditation. The other thing is that we have a new version of Nova where we fixed up some of the issues that we were running into yesterday. So everybody on whatever machine you're working on, go ahead and go to novamodeler.com. It's our webpage.
Are these machines unlocked? Can they do that?
No.
So who's working on personal machines and who's working on workstations? So people on personal machines, you guys can go ahead and do this update.
You can ask to remove the people.
Yeah, that'll take a second, but I think that would be worth doing.
Yeah.
Yeah. So for you guys on personal machines, go ahead and go to our software page. And you'll see that we have our latest build. So I'm going to software, I'm going to downloads. And it'll take a second, but it'll go there. And if you scroll down, you'll see that in our pre-release builds, our pre-release development builds, we have a new Mac build that was released last night. This is software and development. We have a new Windows build, the same build. So depending on what system you're on, you can download that, you can open it up, and you can run it. And that will update your version of Nova. You don't have to relicense or anything like that.
Which one?
The top one. So what we have here is Nova, and this is the build, 594, and then this is the date which it was built and the time that it was built. So that's our February 2nd build, and it's build number 594. And I'll take a second while Ron is setting up the.
Okay. Take maybe just no. I think it worked before you went there, but no, I think it removes everything that you try to install before they remove the bitches. So you maybe you can install it. We'll remove it at the end of the day.
So if I understand that right, anything that gets installed on machines right now at the end of the day gets removed?
I don't know if it's the end of the day or
at some point.
Yeah. When you log out.
12 at night?
Right now he removed the write protection.
Okay. Yeah, so that works. So go ahead and on your workstations download the latest version and run it. I'm going to check that we're all getting there.
Can you say
It's the top one under the Windows build. So the webpage is novamodeler.com/software. And if you scroll down, you'll see Windows builds. Okay. Yeah, so we'll take as long as we need to take to get everything up and running. Computers are rebooting. We won't go scooting ahead without you. While the machines are rebooting, let's talk a little bit about what we're going to try to do. So at the end of the day yesterday, one of our goals was to simulate and plot trajectories in the plane for 100 time steps. For our simple random walk, which is this parameterization, for our correlated, for our biased, and for our biased correlated. So I want to make sure that we get there. Oh, sure. So I want to make sure that everybody is able to do that with the model that is in the Dropbox. So the Dropbox that is shared with the class, you guys have a model there. But before we actually start opening it up and running it. So this is one of the things that we want to do. And I think a lot of you were able to do this. So we'll just take a second and make sure that everybody's all together before we move forward. And then the next thing that we're going to do, and Rich is going to walk us through how to implement this, and we're going to incorporate a new component that we haven't worked with yet in Nova called a code chip. We're going to incorporate a code chip, and we're going to build a method that repeats the above simulation many times. And this is probably more than we'll do. We probably won't repeat the simulation 1,000 times, but we'll repeat it enough to get a sense of what's going on. And we're going to plot some aggregate statistics of the data. And we aren't going to initially plot our MSD. We're going to plot the mean and standard deviation of our step size and of our theta. But we're going to start trying to get to the point where we're generating our simulation data and we're starting to do a little bit of sort of post-processing on our simulation data. And then based on being able to do that with your step sizes and your theta, then you guys, I think, have the equipment necessary to start thinking about how you would actually do it for this quantity, for your MSD. And that'll be the project that we'll do until lunch. And I'll cruise around, and Wayne will cruise around, and Rich will cruise around until we pretty much get to this point. What we'll spend the afternoon doing is we're going to elaborate on this model. So what we have in these movement models are step sizes and theta. That's what we're trying to generate, step sizes and turn angles. And we're going to introduce some more complex functions for developing our step sizes and for developing our turn angles. We'll spend probably the first half of the afternoon session taking the model that we have right now and pulling out the current functions that we have for step size and for theta, and implementing these functions for step size and theta. And what we're preparing ourselves to do is allow our model to have multiple states. So that in one state, we're doing a simple random walk, and then in another state, we're doing a correlated random walk. And the first half of the afternoon will mostly be spent trying to execute that. And we'll do something that feels very similar to what we did yesterday. We're actually going to be using the same general structure and the same general components, but we're going to be switching out bits and pieces. And we're going to be introducing this p-value, or pi actually to be specific. So pi is that state change. If pi is equal to 0, we're doing our simple random walk. If pi is equal to 1, we're doing a correlated random walk. But that's essentially our state, our way to manage our state shift. And we're going to shift at the beginning. We're going to change state just with a simple uniform, probability. We're going to say if a random number between 0 and 1 is less than p, less than whatever our set probability is, we'll switch from one state to another. So we'll spend the first half of the afternoon doing that. We'll get through this. And we'll spend the last part of the afternoon introducing a more expressive function for the way that we change state. So we're going to start with a very simple way of switching from simple random walk to correlated random walk. Just switch back and forth just to get that going. And then we're going to start implementing a more complex form of that exact same process where depending on how many steps you've gone with your simple random walk, the probability of changing to your alternate state increases. Good. Exactly. And then depending on how long you've been going with your correlated random walk, your probability to change state to the other changes as well. But we're going to be building off that same foundation of the model that we had yesterday and that you guys all have out of the Dropbox. So I want to make sure that everybody's able to go find the model in the Dropbox. Is everybody able to go find a model that looks like this? And the right place for it is here. If you guys go to the Dropbox where Wayne shared all of his supporting docs, there will be a NOVA model sitting in there. And I'm noticing that the resolution, this is all very small, right? This is all very small and blurry. When I walk to the back of the class, it's very hard to see that. Does everybody have access to this workshop folder?
We can't really do anything because they're going to restart the computer.
Okay. So I just want to lay out the sort of process while we're booting up. But you guys don't need to do that now. Just know that that's where you're going to go get your model.
Guys, they stressed from the computer center to only install Nova and not do anything else, otherwise the viruses and other things can easily hit the computers. So we'll install Nova and then we'll reinstate the write protection.
Oh, yeah. Did you send me? Yes. I didn't get it. Okay. I have this mail delivery system is very important. So let me just. There. Okay. I will do this right now.
So which build? 594?
594.
Okay.
And you'll see that the date is February 2nd.
All right.
Yeah. Is anybody running into any problems? I'm seeing a lot of people with Nova all loaded up, which is good, and with a model. Seeing most everybody there, so.
But aren't they going to reboot the computer now, or we're
Yeah, they're going to reboot the computer.
Oh.
Once everyone's finished updating, let me know.
80, did you get it? 80?
A question, if we do any other changes, Ron, tomorrow, I don't think it's so bad that at the beginning of every day there isn't a version of Nova installed. If we can download it and have it available for 24 hours, that would probably be
Ask
fine.
them whether that's That's what happens.
Yeah.
I'm not sure what the right protector is.
We're
You're saying the program gets updated faster than the computers get restarted.
But as we said, this is a work in progress.
Yeah. If you ever find yourself on a software development team, you might look back and say, "Oh, I remember a nightly build of Nova way back when. I remember what that was."
I don't know if most of you know the metaphor about seeing sausage made. Sausage can be very delicious, but you never want to see how it's made. So it's the same with Nova.
And politics.
To use Nova is great, but you don't want to see how it's made.
What is the purpose of this exercise?
So so the question in the back was, what's the purpose of our exercise? What's our goal for what are we trying to accomplish today? So in our morning session, I want to make sure that everybody's able to run our different correlated walks. So we have a slider in the model that we just loaded up. You have a slider for A that ranges from 0 to pi. You have a slider for B that has some specified range. It probably ranges from 0 to 1. And I want to make sure that everybody is able to see that as we change our value for pi, our trajectory, the bias or the correlation of our trajectory changes. And as we change our value of B, the bias of our trajectory changes. And so I'll demonstrate what that looks like. Is anybody still getting loaded up with Nova? I want to make sure we have everybody before we get set up.
Everyone finished?
Not quite yet. We'll take another couple minutes. Sorry.
Can I run auto mode and change the slider? Because if I'm trying, it's giving me an error.
So what we have here is we're actually doing the second part. So our slider is now changing the value of I. So A doesn't change based on this slider. It actually now changes based on I, which is our second piece. So you see how I ranges from 0 to 10, and we now have I ranging from 0 to 10. So I think if you put it in auto mode and change I, we'll see our different trajectories. So we're actually doing item number 2.
Okay.
And so I is affecting A.
Yeah,
A is being passed into the model.
And this is
2, part 2. Questions?
Everyone finished updating?
The slider changes I?
Yeah, so we'll talk about that.
Okay.
Yeah.
And this we are not using, right?
Well, we're not using A, but we are using B, and we're using theta hat. So we'll talk about that.
XY plot, there may be a better scale. The scale's a bit makes it too small.
Wide. Okay. Yeah, we can scale it up.
To see what's going on. So on your XY plot, you might want to scale up a bit so you can see more detail.
And on there are more things.
There are more things.
Are you gonna?
Yeah, we'll talk about that. Yeah. So I think we have most everybody. Well, I'll show how to change the scale. So I think we are we? Okay, they're all restarting now.
They're not yet, but it's going to.
It's giving me a lot of noises. No, it's,
Probably tapping on it all the time too.
it's okay. It's better. Thank you.
So I'm going to answer a couple questions while we're waiting for the machines to restart. And I'm going to open up mine as well. So here's my blank canvas. So the first question I got was, what's our slider here? We're actually using a slightly different convention. So before, and in the first part of this model, we're specifying that A and B are constants. So let me roll back here. So in part number 1, simulate and plot trajectories in the plane for 100 steps, where A equals pi, B equals 0. So if we go to our model, you'll see that our A slider isn't actually connected to our movement method. And somebody pointed out that, well, when I start trying to change A, so if I increase A here and I run my model, the first thing I notice is I don't see a change in my XY coordinate data. This decreases. The next thing that somebody pointed out was when I put it in auto mode, which is exactly the kind of tool you would want to use to explore multi-parameter sets, and I change A, I get an error. And the reason why is because we don't have A actually connected up to the A input. So if you want to test your parameters of A and B, remember in Nova you want to you're taking data in, you're putting data out, then open up this chip and pass this A slider in. So that was the first question, is how come A isn't doing anything, and how come when I put it in auto mode and change A I get an error? So that's the first one. So if you want to do the first part of the assignment, or verify that you can do the first part of the assignment, you're going to have to make a modification to your model, which is connecting A directly to your input. So I'll do that after I close and restart here.
So you don't need the slider to be connected to a parameter and the parameter to the model?
You can connect a slider directly as an input into a model. You can do it directly, or you can pass it through a term. You can pass it through some other modifier. Yeah?
Before I'm changing anything, if I'm deleting the A slider, which is not connected, it doesn't affect anything. We don't need it.
So the only reason we have the A slider is because it allows us to control our values of A very specifically for this first part. And what we have in the I component is a way to control our values for A and B more methodically, increasing I from 0 to 10. So we actually have the model set up right now. The model's provided you set up to answer this question. But again, people were looking and saying, well, what I'm used to and what I want to do is I want to just change A and see what happens. And what we notice is that A isn't actually connected. So if you want to connect up A, you can connect it. And if you want to work on this part of it, we actually have the slider already connected up to I. But I want to make sure, I want to take the time in the morning to actually make sure we all know what's going on with our model.
So another recommendation when you're working with models like this is that if you connect up the if you disconnect the A slide and you connect the A parameter, you might want to save that version of the model as your particular version, and then just keep it somewhere, and then take a copy of it and set it up with the parameter with the I that can slide. And the reason for that is if something goes wrong, then you can say you've got your other version saved. So it's good to have, when you mess around with it, rather than messing around with the one that works, make a copy of the one that works and then mess around with another one. That can save you many tears.
And when right before we start with Rich, when we're actually going to be modifying this model and changing this model, I'm going to talk about a couple principles that we should think about for the next couple of weeks. One of them is save early and save often. and save different versions of your file, especially when you're working with in-development software like this. So I want to take a second and I want to resolve the question that was asked, which is an important question. So A isn't connected to anything here. So to connect A, I can open up, and I'm doing a left click on my chip here, on my model, and I'm changing my value, my input value for A from A batch, which is what is connected to I, and I'm changing it directly to A. And now when I run my model, it should allow me to go into auto mode and change my value of A. Oh, put a test on. Well, ideally it would. But so we'll skip over that one and we'll just work on changing the value of I. So I'll close this.
Even when the slider is connected, when you change it, it really changes the plot. So it's kind of strange. So you see, it's not connected. But when I change it, it changes.
So do you think that changes is? I would suspect that might be a sufficient amount of stochasticity just from the other values in our model.
Where do you have your stochasticity?
We're actually affecting a value of A there.
I have a problem with the hot slider. Every time I put it, there's an error. And I need to close it.
Yeah, so I'm getting something similar.
With the theta hash? Because all data is run.
I'm getting it.
When I do it in auto.
But I was saying commits, but
Let me look at something actually. Okay. Yeah, I'm seeing the consistency. I might know how to fix that one. So I'm noticing that a lot of people, when they're moving their sliders around in auto mode, some people are getting errors. I was getting some here, you guys are getting some there. So I'm going to take a quick second and look at something and see if I can update our version of our model and put it back in the Dropbox and you guys can open it up.
That's animal. Automatically change the structures. Automatically change the now we need to run again. אבל כן, כן, אבל צריך קודם לעשות טבלה של מיצפות אז יש פה כל הנושאים וכל הרעם. כן.
עשית משהו, נכון? זה התחילה.
זה בשביל דבר לחבר. כן?
תחילה. גם אני.
לא.
פשוט זה אף.
זה ההיטליס.
אבל זה עושה שאתה לא... שזה כל פעם נמחק.
אבל לא, ברור.
לא, אני עבדתי על ההסברה שלי פה.
שנה? האי עולה, כשאת עושה לו לעשות תור איי עד משהו, את יכולה לעשות כל מה שאת רוצה, בלי קשר, את עושה לך את זה כאן. לא? לא, באמת אני מסתכל
So I'm gonna point out two things. Number one, since we're using a shared file on the Dropbox, what I would recommend for everybody is to actually copy that file onto their local system. Because I noticed while I was working on it that somebody probably saved it on their side and they were working on the same version I was. And so it's saved over this one. So I've added a new one, which is the original. So please work on your local machines, copy and paste that or drag, copy, you have to copy it. If you drag and drop it, you'll pull it out of the shared Dropbox and it'll end up on your machine. So copy and paste it onto your local machine and work on a local version, a local copy. And we'll keep this original one as our base version. So that's number one. Number two is, any questions? Number two is I'm getting the exact same errors that you are getting. So when I attach the A slider in and I replace the batch slider with the A slider, I get a crash. I think that's something that we have to work out on the back end. So I'm gonna jump to part two, which is the way the model is set up right now, where you can actually slide through I values and you can progressively see how your movement trajectories change in response to different values of A that way. So I'll demonstrate that. Yes?
download the original one?
Whatever you're working on in your machines, I'm sure is fine, because you're working with a version of that. But in the future, or actually before we start with Rich, I would like everybody to copy that original one, because this one just got modified, so I'm not sure what happened to it.
The original one is the same as the first one?
The original is the same as the first one, exactly right. Question?
No, I don't know if this solves the problem, but what I noticed is that if I do capture load and then init and start the auto mode, then it crashes. But if I do capture load exec and then do the auto mode, then it will respond. Maybe it's just me.
So I'll jot a note down on this one because I think we have to track this one down on the backside. But when you step it,
First exec and then...
If I don't do exec, I do init. If I want to go to step by step and then I move the slider, it crashes. But if I don't go to init, I just do exec.
And then you move the slider?
Play with the slider, it works.
Okay, I'll jot that note down and that'll probably help us figure out what's going on. Okay, so what we're going to do is we're going to look at this second question since we ran into an issue with this top one. So we're going to repeat the above simulation and we're going to be running over, we're going to repeat it a couple times. We aren't going to repeat it 1,000 times and we aren't yet going to generate our MSD. Rich is going to work with us on that one and get us closer to that. But we're going to methodically vary our parameter I from a value of 0 to 10, which means that A is going to range from a value of 0 to pi. And we're using auto mode, we're going to be able to see our trajectory get more correlated as our I value changes. So our initial value for our I slider is going to be 10. I'm going to execute our model here. I'm going to put it into auto mode. And as I decreases, we're going to see that the trajectory becomes more directionally correlated. So the step sizes are actually longer in one direction than another. And I can execute this a couple times with I equal to 1. And we'll see that in 100 time steps, the distance that we travel is further. And when I increase I, as I approaches 10, so as I approaches 10, so as I ranges from 0 to 10, if I is equal to 10, what is A equal to? So A is equal to pi if I is equal to 10. And when A is equal to pi, we see that our walk approaches a random walk. This looks more like Brownian motion than something that's correlated or directed. Yeah, so to zoom in, so one of the questions was, can we blow it up a little bit more? We can zoom in on this by scrolling over it. And if we zoom in on it, we see that we're staying pretty local. Let's try to see if there's some intuition behind why, if A is equal to pi, our random walk stays very local. And we'll go down to our submodel and we'll see if that makes sense to us. So I'm going to go down to our submodel. And you can see that our submodel is a little bit different than it was yesterday. And I'll zoom in a little bit since I think this is pretty small.
I'm getting quite a lot of errors.
You are?
Just letting you know.
Okay. So our theta, our turn angle, is a function, is just theta plus some random interval. And our random interval is a value between A and negative A. So this means that if A is equal to pi, our theta, our turn angle at any given time step is going to be randomly anywhere, a random modification anywhere inside of our unit circle. So this makes sense that if A is equal to pi, we're looking at a random walk, a simple random walk that's very localized. And that as A decreases to 0, we're progressively looking at a random walk that is more correlated, more directional. So that's step 1. If we go back to our goals here, we wanted to repeat the above simulations many times. We haven't plotted our MSDs yet, but we're getting an intuition for the fact that as A approaches pi, our random walks become more random, and as A approaches 0, our random walks become more directed. So then the next one is changing our value of B. So holding some value of A constant, if we change our value of B in range between I of 0 to 10, we're going to see more bias in our random walks. And so the way we're going to implement that is we're going to go up to our top level model, and we're going to reconnect things. And I hope we don't run into this same issue that we were running into before, but what I would like to do is I'd like to connect A as a constant into our chip, and I'd like to connect B batch. So now we're going to be iterating through values of I to B and pass that value into our B input. So essentially we're swapping out our iterative input into A and making A a constant, and we're now putting an iterative input into B.
Just leave the slider on a constant, not touch it?
You can leave a slider on a constant and not touch it. Yeah, exactly. So if you wanted to replace A with a term that was just a constant, that would be synonymous to plugging the slider in as well, if I understand your question. Is everybody, are we following? Are we okay? Kind of? We're using an integer I to go through different parameter sets of A, which we just looked at, and we saw behavior that changed as we went through different parameter sets. And we're going to use I to go through different parameter sets of B as well and observe that change. So this is going to be our reconnecting. We're going to be unconnecting, we're going to be disconnecting B from a slider, and we're going to be connecting batch B. So I'm going to go to our chip here, and I'm going to step through the different inputs. So this is asking for what input we have for A, and we're adding in A batch. I'd like to change this to the A slider. So our slider A is different from A batch. So if I click on this, we're now connecting our A slider as our input into our model. And I'm going to scroll through the other inputs into the model. So another one of our inputs is theta hat. We are going to leave that as a constant. And now we have B, and we're going to replace the B input, which is a slider, to the batched value. And I'm going to hit OK. And you'll see that our inputs into our chip just changed. So I'm going to circle around and make sure that everybody's able to get that one, because we're going to be working with chips a lot, and so you're going to want to be able to add and change your inputs and edit your inputs as you go along. So here it's asking for what value A is going to take as an input. And so the value that you would want to input for A is the slider value A. So that's our slider.
Oh, wait, do you want him to be connected?
Yeah, because we're now replacing our batch process. We're instead of iterating over values of A, we're going to be iterating over values of B. And so A is going to stay a constant.
Okay.
And B is now going to be a function of I, if that makes sense.
So I want A to be connected?
Yeah.
And B batch?
Yeah, so you have A connected to A, and then we can scroll through the other inputs if you click up on that arrow. So theta hat is theta hat, and now we want B to actually be connected to B batch. And that's on your output side, so you actually want to select there on that one, and then make sure that your out theta is none. So now, when we hit OK, what will change in the image?
B batch will be connected from the left side.
Okay, and what else?
And A would be connected also to here.
Anything else?
and this would be disconnected.
Okay. So
my question is, why, if we have these graphs from the output, why are they not here?
So that was something that we ran into yesterday, where our batch mode operation, which we were trying to do yesterday, required that these plots were pinned. But you, I think by and large, you can actually use those output pins to graph the values. Yeah. Questions?
It was her question.
So I'll answer it here, and then I'll answer it with the group as well. So there's two ways to plot data when you're working in a hierarchy. And I'll draw a picture of this. So we built a submodel, right? And that submodel, we could run it all alone. Like, we didn't need our main model space. We could run that model, and we could plot things in that model, right? So let's go down to our submodel. If you notice, theta, s, x, and y are all being passed to plots. So the plots that we're looking at here are actually the submodel plots.
Why you need to show
That's a totally great question. We have these because we had another implementation of this model that had them as outputs, and we also wanted to show
plots or the pins?
The output, the actual pins. So why do we have these if we aren't using them, right?
Because if you don't have them, you still see the output.
Yeah. So these aren't integral right now, but what we wanted to show yesterday is that you have a submodel, and data goes in and runs through a simulation, runs through a process, and data comes out. And that input pins and output pins are one way to do that.
If you don't have them,
the model would run fine.
It would run anyway.
Yeah, exactly.
But in some cases you need them.
It's two ways of doing the same thing. So the information that we're getting, right, is theta, s, x, and y. And we're getting it directly here.
Yes.
And these graphs are actually at the lower level.
And they have to be at the lower level.
They don't have to be.
No?
Yeah, so
If you want to just see the lower level working and you don't have graph, then you need to have.
So if you want to see what's going on at the lower level, you can plot them here. But you could also go up to the top level and plot them based on the output pins.
So if you connect a graph to each of them, you will see, and you don't have them in the lower level, you will see them. So it's like just an extra.
Similar way of, a different way of doing the same thing. And the reason why is that when you're working hierarchically, you work in that lower level environment, the bottom level, and you plot things there. But then you can take that lower level object and you can encapsulate it and bring it up to the top. And sometimes you want to get information out of that top level, which is why you have pins. So that's
It's just in case you want to see just the top level.
And you'll see that there are reasons why we do that. I think Rich will walk us through something that uses these pins to.
So if you have several chips, you want to take only one of the outputs from each.
Or say you had a population of individuals, right? So we're only looking at one individual that's moving around, but say we had 50 individuals and we wanted to look at some statistic that is an aggregate of all of them. So take 50 individuals and look at, what position they're at or something like that. What's happening is that we have a local level model, and then we have a larger level model on top of that, and we want to be able to get information out of that larger level model. We don't want to get information necessarily out of that bottom level model. We want to get something that's an aggregate.
The graphs on the lower level, you will always get it.
You will.
But you can add an extra graph only on the top level and look at the integrated graph. I don't know what to say, right?
Yeah, I mean, at the higher level, you're looking at slightly different things usually, and pins are a way to look at that output information.
Okay. But if you have like several chips and you have the graphs at the lower level, then you will have lots of graphs.
So that's an interesting nuance. If you have graphs at the lower level, but you have lots of chips, the lower level is only ever going to be showing you data on one of your chips. Yeah, exactly.
Are all these outputs?
Yeah. So for every output pin.
Why can't I see them here?
Well, you can, all four.
Oh, but I can't see them connected.
They aren't connected to anything.
Okay. So why won't this be just none? Why can I see four things?
So if you scroll up to the top, you'll see that one of our outputs is out Y, right? That's actually that top pin. If you keep on scrolling, how X is that pin, how S is that pin, how theta is that pin. And if you go down to our submodel, click it, give it another click, you'll see that we have 4 output pins. So these 4 pins actually correspond to the 4 pins up at the top.
And you leave none because you connect.
Yeah, because we aren't doing anything with that data.
Connect that to the graph.
Yeah, exactly. So I just got a really, really good question that I'd like to answer before we move on to our parameterizations for B, and then that'll be the last thing that we do before we work a little bit with Rich. And actually, I'll use, if I can, so the question was, why do we have output pins on our chip here that are not connected to anything? So if you notice, we're plotting theta, right? But up at our top level here, one of those pins is actually theta, output of theta. Which one is it? I think it's that one, top one. So we actually have an output pin for theta, but it's not connected to anything. That's strange, right? Why would you have an output pin that's not connected to anything?
The graph is,
This is great that you guys are able to see this. So this graph, you guys immediately say, is actually inside this chip. That if you opened up this chip, you would see our model, and one of the things that we would have is theta in there.
But it will only show here if you pin it down, right?
So it only shows if you pin it down. And this is what hierarchical modeling is all about. In part, this is one of the major things that we can do.
So pinning it down makes it global.
So pinning it down, the question was, pinning it down makes it global. Pinning it down keeps the graph in your display regardless of what hierarchical level you're at. So,
Not below.
but not below. It won't go below. So a conceptual way of thinking about what our model is we have our lower level model, and it has stocks and flows in it. It has theta. We'll just stick with theta, but that could be any value. That could be X or S or Y. And if you go down and look at that bottom level, you'll see that there's a little connector to a plot, right? And what we're actually plotting down at that lower level is the value for theta. And we're plotting at that lower level. We actually started by prototyping our model at that local level. And then we wanted to implement this model in a larger hierarchical model space. And so we built something bigger. And we took our submodel and we put it up here. But what happens is if we didn't pin our graph, so yesterday we spent a little bit of time figuring out what it means to pin a graph. What essentially we're doing when we're pinning a graph is we're saying that whatever we plotted down here, stick it into our viewer so that when we go up to this top level, we actually still have that plot at the lower level so that this is consistent between both levels. The reason why we have input pins and output pins, and everybody pointed out this looks redundant, right? Here I have output pins. Why do I need those? And the answer is you don't. If you went through and you got rid of all your output pins, you would still be able to visualize. Because what you're visualizing is actually data at the lower level that's being persistent up at the top. An alternate way to visualize the exact same data would be to take this theta pin and connect it to a plot. And what you would be getting, and the plot that you would get up here would be unpinned. So you would actually have another plot of theta, and it wouldn't be pinned. It wouldn't be stuck down. So this is always an important thing as you're building your models hierarchically. In your head, you're kind of conceptualizing things that happen at this lower level, and then things that happen at the upper level. And by and large, the typical convention is to use pins to look at your data rather than necessarily pinning a graph. And we're using pins in two different languages. But to use output pins instead of actually, tacking your plot to your visual space. So I'm pretty sure when Rich demos his stuff and all, we'll do one more thing and then I'll pass it over to him. We're actually going to use those output pins. So instead of pinning the data down here, we're actually going to be using output pins, and you're going to see some of the things that we can do when we actually implement our submodel in a larger model space. And that's going to be some of the sort of aggregate statistics. So the last thing I want to do, just to make sure we're complete and clear, is I want to try to go ahead and run this. So we changed our inputs and our outputs. We're now passing b as a function of I into our b input, and we're passing the constant a just from our slider into our a input. So our a is constant now, and our b is going to be based on I. I'm going to go ahead and give this a run, and if we don't get this, it'll be okay, and I'll pass it over to Rich. We might run into some errors, but what we should expect to see is as we change I, we're going to see different behavior in our random walk. Is there a question?
Why do we need our b connected to I? Why can't we just play with it?
You absolutely could. So the reason why I did this is that the specification of the assignment asks for something that's defined in terms of I. And a way to implement that is to have I as a slider so that the thing you're changing is I, and then I is an input to this function for A. So you absolutely could set up A, and you could give A a range of 0 to 10 times A to, I guess in this case, right, so we're looking at B now. So at 0, when I equals 0, then B is equal to 0. And when I is equal to 10, B is equal to 0.5. You could set a slider up that ranged from 0 to 0.5, and you could look at the values that way, certainly. But we're using I to maintain this same convention.
I think if I could just answer that, in order to write down the mathematics, it's convenient to say B is equal to something times this index I. But when you code it up, you can just go to B and say under batch, you can let B range in value. So, but to write that down mathematically is not so easy. You've got to use words and things. Whereas if you want to make it a formula in mathematics, then you have to use the I.
The other reason to do this additionally is to understand that your inputs into your chip can be anything. It doesn't necessarily need to be a slider. It can be a term that's a constant, or it can be a term that's a function of another term that's a function of a slider. The fact that these components can be combined and recombined to actually lead to input data. So let's go ahead and give this a shot, and we'll cross our fingers and hope we see what we want to see. And if we don't, I'll open this up and we'll run this with Rich. So here I'm executing our model. So our value for A, for our, let me slide back over here. So notice that in the instructions it doesn't give you a constant value for A. It doesn't specify what constant value for A that you might want to use. But in part number 1, it says that a correlated random walk is going to have a value of A that is less than pi. Notice that our biased correlated random walk is a value of A that is pi divided by 4, so a value less than 5, and a value of B that's 0.1. So to get a biased correlated random walk, you can set A, the constant value of A, to 1/4 of pi, and then B will change based on I. B will range across these values. And for our biased random walk, set A equal to pi, constant value pi, and then B will range across these values. So really, the simple random walk, the correlated random walk, the biased random walk, and the biased correlated random walk, they're just different parameterizations of these of A and B. So I'm going to go ahead and jump, and we'll go ahead and do our biased correlated random walk. So I'm going to set A to 1/4 pi, and then B will be determined by our function I. So 1/4 pi is about 0.78. And here's our value for I. So I'm going to put this into auto mode. And I'm going to decrease our value for I. And what do we notice in our paths? What sensitivities do we notice as we increase and decrease I? I'll run this. And this is just observation. So what do you see?
More direction.
More directional?
Increase or as we decrease?
Yeah, so let's think about what happens to our value for B. Well, which direction do you want to go in?
I'll get that.
So what do we see? So when I is 10, what value for B do we have? 0.5. And when I is 0, what value for B do we have? We have 0. So B is ranging from a value of 0 to 0.5. And so what we notice is as B increases, which is increasing our value for I, as B increases, we see more directionality to our movement.
You better restart.
Say what?
You better restart.
Oh no, what did I click? Anyway, let's go ahead and wrap this up. But you have, in this model, you have the ability to do what was in that second part of that first assignment. And that's one of the things that we wanted to make sure that everybody got to this sort of checkpoint, where we're clear on the fact that inputs are A and B, and those determine whether we're working with correlated random walks, biased random walks, biased correlated random walks, and that we can look over multiple parameter sets. And then inside of all that, understanding how NOVA components work and how some of our hierarchy works. So I think if we're not perfectly clear, we're at least at a place where we've done something and we know a little bit more about what we've done, rather than having a model that we don't necessarily understand.
Can you show again how to increase you started from I equal to 0 and you go to I equal to 10?
Yeah.
And you just do that by selecting init every time? No, set every time?
I actually put it into auto mode.
And then you click one.
Yeah, and then as I was changing my values for I, yeah, it updated. And then if for any one of these parameterizations, if I wanted to see a couple more simulations of it with that parameter set, I could execute the model again. Because there's stochasticity involved here, right? When we did this run, we ended up at this position, but we saw that with the same parameter set, we might end up, backwards in a lot of different other places. So we are working with probability distributions, and it's stochastic. So I'll go ahead and pass this off to Rich and try to get Rich set up. And what Rich is going to do is he's going to walk you through a method to start generating aggregate statistics. So we're going to work on a way of running this model multiple times with a given parameter set and looking at what the general trends are in the data. So doing some statistical analysis on larger volumes of data that we're generating. And something that Wayne has said a couple times but might not be super clear is that this is actually how you have to assess and explore these models, is that you generate a lot of data based on a stochastic process or a distribution, and then you're looking at some statistics on that large volume of data that you generated and comparing that to data, empirical animal movement data, or comparing that to simulation data that's generated by other distributions. But this is working our way to doing the kind of modeling at the kind of volumes that we need to do to compare our simulation data to empirical data, or simulation data from one distribution to simulation data from another distribution. So Rich will start us on that. And we aren't going to get necessarily to our MSDs, but we are going to look at means and standard deviations of our step size and of our turning angle.
Okay, first, while I'm setting up, let me say each of the 4 or 5 people who emailed me models yesterday, I have replied with working versions. Some of you, we've already worked those things out. First, I want to apologize for what really were some omissions on our part. The good news is that the problems were all kind of uniform. That there were basically three things that we omitted in discussing the batch. It was really, I can't, all I can say is that, I again apologize for that. One.
Sorry.
Oh, sure.
And while Rich is talking, I'm going to be cruising around and answering questions.
Yeah, the first thing is that you have to pin, I mean, these are all things that you know, but I'll just reiterate them. That when you use batch mode, you have to pin the graphs that are going to be collecting the data. That's really a technical point, though it will probably be in a later version of Nova, sort of an automatic pinning, where it will detect that you're doing this and will just automatically do it, but we don't have that yet. That was probably the biggest problem. The second problem that popped up, and this should have been something that Nova noticed, but that is if you put spaces in the names of models, especially the top level model, and then save it, that causes some serious problems too. Again, I thought I had worked it out so that Nova would detect that and put the underscore in for you, but apparently not at the top level. So that was a second error. Again, this is nobody's fault because we didn't say anything about it. The third thing is that when you're running in batch mode, especially if the model underneath is fairly complex and there's a lot going on, you have to lower the speedometer because there's a speed bar at the top. I'll show it to you so that it doesn't run so fast. If you try to run it very fast in batch, it'll crash and it'll just freeze up. Okay? So those three things, certainly for the ones that were sent to me, those were the three. It was one or more of those oversights and nothing else. So the good news is that at least the problem is not all over the map. It's contained. We know what it is, and we know how to address it. And hopefully, we won't see that again. We might see something else, but it isn't. It is something that's quite rational in a sense. So what I'm going to do? I've worked through this twice now, and I'm certain that we will be able to get this to work because I was able to do it. As I said, I was able to do it twice with two completely separate efforts. So I will show you first what we're trying to achieve, and then together we will work and take the prototype model that Nick distributed and work that into this to add these new functionalities. So let me first get myself a little set up, and then we can start.
While Richard is setting up, there's one thing I wanted to say to you that we can appreciate very much, and that is feedback. And if you want to make comments at this point, and just keep a list of comments that you're going to give us at the end of the workshop. If you want to email anything to us while the workshop is ongoing, please do so. At the end of the workshop, we hope to put a survey online to get feedback from you about how this went. So as you go through, you can think, oh, this sucks, I'm just telling them about it, or this is great, I'm going to tell them it works. Right?
This, Ron?
These ideas in your mind.
There's no.
How this is working for you.
This won't go into the one that's open there. It doesn't fit.
Let me see.
The holes are not in the right place. Just go back here for a second. was supposed to go diagonally, I guess. All right. Come on, wake up, wake up, wake up. Hello. Okay. Do we want to lower the lights? Can you see? Should we lower the lights a little bit here? What is that?
The lights are there for other stuff.
Okay, so this, just to remind you, this of course is the model, the prototype that you folks were looking at. Am I right? Everybody has a copy of this. And so we run that, and each time we run that, we get another run, and we have the graphs set up to collect the runs, and we can, eyeball what's going on here in terms of the variation that we get in the runs, but we, of course, are not measuring anything precisely, and that's what we want to change. We want to be able to make some precise measurements on what kind of averaging and what kind of average and variation we are seeing in those runs. So we're going to do a couple of things to make that happen, and I'm not going to show you the result. So I'm going to show you where we're going to. And so I can find it. So this looks like it's the same exact. This is almost exactly the same. I've done a few things though to change it. And most importantly, I've added two graphs, and I don't have a lot of room here, so I added the graphs over here. So now, when I load this, what we're going to see is we're going to see multiple runs, and we're going to see statistics accumulated. So I'm going to just run it once. Okay, so there's the first run. I just did one whole run, and there should look familiar to you there as being a run. I'll now do a second run, and what we're seeing in these new graphs are three values. We're seeing the mean, which is blue. We're seeing plus the mean plus the standard deviation, which is green. And we're seeing the mean minus the standard deviation, which is red. Now, this is the speed slider that I was talking about. That varies the speed of the simulation. And so so I've cranked it back quite a bit.
Sorry, Richard, if the connection's not right, this is not bright, so maybe let's just, can I just do this and see if it's bright enough?
Now it's nothing.
No, it'll come. It's not. Can you see it's kind of gone down?
Yeah, I can see. It's stunk.
Let's just try all these connections.
Can we brighten it?
So I had a question back here, which was, is every step that Rich was running in this version of the simulation 1,000 iterations?
I think it's 100.
Of 100 steps?
No, every step I'm running here is one iteration of 100 steps, and each time I run it, I'm getting another iteration of that.
So every run is 100 steps, but we're retaining that data.
Right. And we're now,
Run the model.
so you'll notice, look what's happening to the accumulated statistics.
What statistic is right?
Yes.
The adapter. Maybe you can change the adapter.
Yeah, it's not. Yeah. This is really annoying with the adapter.
Well, I have another adapter if you want to try it.
I don't know.
Try replacing the adapter.
So should you guys have a model open right now that's doing this? And the answer is no, not yet. So we're just showing you what we're going to get to. This is going to be the end result that we're looking for. And we're going to build in some other higher level tools that take data from a chip, from a run, from a simulation of 100 steps, and actually retain that data so that every time you're executing your 100-step model, you're actually holding on to that information and you're able to run statistics on that information. And that's what we're just showing. So he's taking the mean and the standard deviation of every run that's been completed so far.
Well, I'll show you. If you want to run 1,000 steps, I mean, here's what it'll be. If this,
Well, I don't think the question was.
this is as bright as I can get it.
Richard, if this is just one iteration of 100 time steps,
Yes. Each time I'm clicking it, it's one iteration of 100 time steps.
then what's the standard deviation of?
The standard deviation is across well, the first time it's going to be empty.
Okay. So it's
Right.
accumulating.
It's accumulating.
And doing standard deviation on all the iterations that you've passed.
Right, well, like here's the first one. All right, so the first one, of course, there's no standard deviation. Well, unfortunately, I'm executing it here.
It's smoothing out as you do the runs.
So look, there's no standard deviation because it's just one.
Right.
So now I've got 2, and so there's some. I mean, isn't that what we wanted?
Yes.
Yeah.
Exactly right.
This is what you were asking me about yesterday, and now we're doing it. So, and now if I hit run now, I won't have 1,000 runs. I'm going to have somewhere close to 100 runs. As you can see the clock running there. So you can get 1,000 runs by just letting this go.
And you can see it smoothing out as you get more runs.
Right.
And I want to point out which plot is which, because it's hard to tell with the resolution of the screen. So this top plot is our step size. So this is the distribution, the mean and standard deviation of our step size given the parameterization that we're using. And we don't see what the parameterization is. And this is the mean and standard deviation of our turning wheel. So the green is one standard deviation from the mean?
Yeah, so the mean is the blue, and the red is minus the standard deviation, and the green is plus the standard deviation.
Yeah, so you have mean and then a bound, like an error. The x-axis is step numbers, time. So
there's no agreement to average of steps from.
So this is your mean square displacement of
Step
time.
number 901 differ from
the way that I would think about it is steps 1 through 100 for run 1. Step 1 through 100, run 2. Step 1 through 100 for run 2.
have 1 point now, right?
You're actually, right, so at point 50, you're averaging all the values for point 50, and that's your mean at point 5, at 50.
What I'm asking is why is that more interesting than just averaging all of the steps from 0 to 100 in each run?
Well, because we're plotting the means, we're plotting the displacement after 1 time step, the displacement after 2 time steps, the displacement after 3. I don't know what, are you plotting displacement there or what?
We're doing step size.
We're doing step size right now.
Oh, yeah, then it's, I thought, are you?
We're starting with step size and angle as the.
Oh, okay, yeah. You're right. Yeah. When we do the mean, so we're setting this up so we can see the mean squared displacement over time, which will follow a square root shape as if it's a pure random walk, and then it should lengthen up and become proportional to time. Then it becomes
This is even worse now.
yeah, I don't know why this is not giving a bright signal anymore.
It was the same as
There. That's better.
Okay, nobody breathe. Okay, so does everyone see where we're going with this? Does this make sense to people? Do you like it?
So it's 100 runs of each 100 steps, yes?
Yes. 100 runs of 100 steps and then looking at the variation.
Is it? Yeah, so
This is what you wanted.
right, except we don't want, we want to run it with distance rather than
Then S?
Yeah, then S. You don't want to run it with S.
Well, he said S.
We want to run it with distance.
Well, do we have distance coming out of there?
You can run it with either X or Y. Is more interesting than S.
Well, we'll add a third one. We'll add X and we'll add Y. We'll just put Femoro on. It's easy to put them on.
We've got to calculate the square root of X squared plus Y squared.
Well, why don't we do this now and we'll do the other one after lunch, all right? Because the process is once you've got the idea of how to do this, it's going to be easy. Okay? So I'm going to take you through it step by step on how to add this, and you won't even have to look at one bit of code. The code is all going to be mysteriously hidden. Okay, so now I'm going back to my earlier file. I'm going back.
Something happened.
Never mind, it's bluish.
So it's bluish. Everybody in this room is bluish.
People are confused.
Huh?
Because it's on step size.
Yeah.
Because it doesn't change with time, really.
Well, do you want me to do it with X and Y instead?
Just do it with.
Let's do it with theta now, and then we'll do it with X and Y.
Just do it X or Y.
All right.
It's more interesting than step size.
Okay. Let's try it. We'll do it give it a shot here.
Yeah. So, because you can pull either one of those out.
Yeah. Can everyone see this, even though it's turned blue?
Yeah.
So I think there was a good cascade of questions. So the first question was, well, why is this interesting to look at the mean and standard deviation of step size? And Wayne's answer was, well, it's not actually that interesting. And then we're thinking about other measures of our simulation that we want to explore in sort of an aggregate statistical form. And one of them is mean squared displacement. So as we're working through these examples, the general concept is that we're giving you a tool, and we're building a tool in Nova that allows you to look at aggregate statistics. What those aggregate statistics are up to you in the implementation, and we'll walk you through a couple of them. But the simplest one that we can implement is the mean and standard deviation of step size or of turning. And the mean squared displacement is one step beyond that. But I think that's an interesting conversation. Really what the power of what we're doing here is giving you a tool that can take in streams of data, that can take in multiple iterations of simulation, and then take that data and operate on it in some form, and then give you output. And this is an example of that kind of workflow.
So one of the other things we can pull out instead of step size is distance X. And that should be more interesting, or distance Y. Is it distance that you got on the X-axis or distance that you got on the Y? The most interesting, of course, is the actual deviation, which is the square root of X squared plus Y squared. So we have to put the X and Y information to turn it into...
But we can probably get that.
Yeah. So the power here is that we actually have factored this process out, right? We aren't writing one function that's going to give us our MSD. We're actually writing a tool that takes in data, processes it.
All right, let's get started with it, or else we'll never get done. All right, so the first thing we have to do, okay, now the first thing we're going to do is save this under a different name, because you're going to, if you ruin it, you don't want to have to, you know. So we're going to go to File, we're going to go to Save As, and we're going to say save it as, WS Final with.
But save it locally on your own desktop.
Yeah, on your own machine,
yeah.
not in the clipboard.
But not also on the desktop, because when we go to lunch.
Yeah, that's another problem. Just save it somewhere you know you can get it. All right, so I'm calling it with stats. You can call it anything you want, but just save it with another name, so that in case we are hopelessly screwed up, we can always go back to square one. All right, now the second thing we want to do is we're going to change the nature of the simulation. We're going to turn this chip into a clocked chip. Now a clock chip is like batch mode. What it does is each time the clock ticks on the top level, you get one run at the lower level. And I'll actually show that to you as soon as we do this. So to change this into a clock chip, you right click on it, just like this, and you see it says clocked question mark on the right. Now check that, and it already happens that, at least on my machine here, it says start 0, end 100 with a dt of 1 method discrete. It's already set up exactly the way we want it, so I don't have to change that. But all that does is it says what the clock now inside that chip should be like.
So it means that every time you do a step?
Every time you do a step here, you go 100 times down there. Okay? And I'll show that to you, because now, as soon as we do that, hit OK, and now do capture, load, and now you definitely have to pull the speed down, okay, to about here. Because you can get, now the first thing I'm going to do is I'm going to save this. I'm saving it now. Now I'll do capture, load, and then init, okay. And now I'm going to, instead of doing run or exec, I'm just going to do step. Now that's like one step at this level. But one step at this level is 100 steps at the lower level. So I click step, and I get a whole run. If I click step again, I get another run.
And what is current?
I'm sorry? Oh, current is the number of steps at the top level. So we've changed our we've changed our calibration of time. So that one step up here is 100 steps down there. And I could just keep clicking this step, 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 step. Or I could go, I can restart it. You hit load to restart it and click exec, and I'll get my 100 steps.
Richard?
Yes?
What happens with the batch process now?
We're not using the batch process now, are we?
No.
No.
You're supposed to be using it.
Well, we'll figure out how that figures in later. That creates another level up. We might be able to do the batch process too.
Okay.
Let's ignore that for now.
But currently, one of the inputs.
The I is fixed. We're just running it 100 times with the same value of I.
So A and B are both constants. B is a function of I, and I is a constant.
Right. So we're just running it. We're running with the same parameters over and over again.
There is no batch processing.
There is no batch processing at this point. Okay. So if I do load, you remember you do load to reset the graphs. Okay. So we've already, with a very, very simple change, you'll notice we've done something quite profound. Right? We've changed the whole nature of what we're calling a step and what we're calling an execution. Okay, we've really lifted it to another level. Okay, so that it was a very, as you can see, it was a very simple thing to do. Does it work for everybody? Okay, no problems there. Okay, yes.
What does the start mean when you check the clock? End means how many times you want it to run.
Start means the starting time on the clock of that. It's almost always 0.
What meaning should it have if it starts from 5?
Well, in some models it might. Okay. We've never had any models like that, but they might, you might have. Actually, you're right. It really doesn't matter because it's by itself. So it does seem kind of useless, but.
It doesn't matter what time.
Right.
Start from you put it.
Well, no, because you may be using time in the model. In other words, time might actually be a parameter to the model, in which case sort of an absolute time, not just a counting of steps, might actually be important.
So then it would start running it from 0, but not show you the output, and only start showing you the output from 5?
No, it'll start running it at 5. If you want to go from 5 to 25, the thing called time will be 5 to 25. And the graphs will go 5 to 25. Okay? All right. Good question, but
maybe I could answer that. Maybe if time is linked to a season, so that time is January and you wanted to start something in March, and in your description, your equations actually include something called TIME capitalized, because maybe you have a sinusoidal wave in there that tells you how much grass there is or how much rain at a certain time. Then you might want to have this run, have a variable time inside that takes certain values that link to the sine function.
There would be a way to work around this if we just used, we may have to be rethinking this because we've linked time, the concept of time to iterations, but the concept of time and iterations may not necessarily coincide. We might have a whole new different, time might just be a variable, as Blaine points out, that starts 5 later than where you're actually starting. So, I mean, ultimately, we may change the whole thing. But for now, just always keep the start at 0 and it won't be a problem. Okay, so I ran my 100 versions. If I wanted to wait and go 1,000, I could get 1,000. Okay, so we have our 1,000 or 100 steps. What we don't have is we don't have any statistics on this yet. We have the collection of outputs, and we want to measure the statistics. All right, so here's the thing that makes this complicated. It's not complicated, but that makes this a little more complicated than otherwise. And that is, when you're measuring statistics, what you're doing is you're taking a whole run, and you're measuring the statistics across that, you know, and in some sense, in cross-section at each point of time, and presenting that as a graph. That's what we saw before. So what we need to do is we need to deliver a data structure called run data, which is actually a snapshot of the complete run. So if I just go back to this, if I just start it again, I do one step, okay, that's a run. That's one run. A run consists of 100 points. This thing has to deliver 100 points to the averager so that it knows how to work with those points. Now, the beauty of this is I'm going to give you 2 code chips that manage this, and all you really have to know is how to hook those code chips in. If you are curious on how it works, you can look at the code chips, and I'm happy to sit down with anybody who is interested and explain what's going on. It's not that I don't want you to know what's going on. It's that to do this, you don't have to know what's going on. You just have to know how to do it. Okay? Now, this is because there are people who really don't care how it works. They just want to get the results. And there are people who are interested in results. There are people who are interested in methodology. The whole point of NOVA is that you can be as involved in the design work as you want to be. But not wanting to be involved in that level of design doesn't prohibit you from using the tool. So, I have put something into the Dropbox that I want to tell you about. While you were listening to Wayne and Nick, if you open the Dropbox, here's my Dropbox, here it is. And this is it. You'll see that there's something called ws1avg.cmp. Can everyone see that? It's this thing here. And what I need you to do is copy this to the same place as you have your file. It's a very small file. It's only 1 kilobyte. Copy that down into the same directory where everything else is. I'll wait a second until you get that done. Okay, are we there yet? Everyone ready? Can I go on? All right. So now I'm back to the model. Okay, so has everybody been able to do what I've been able to do so far? Everybody's been able to do that with the clock chip. Okay. So now we're going to add code chips to our model. Okay. So go to the, we're going to first go to the submodel. So click on SRW. And let's get down there, because we're going to do some modifications to this to make this work. We have to do modifications down here, and we have to do modifications on the top. So if you open the code chip palette, it should be empty, because we're not using any code chips. Does everyone find the code chip palette? You didn't find it? Taryn? You want to?
Where is it?
The code chip palette is right next to the plugins palette, which is right next to the components palette on the top.
It's the top menu there.
On the top menu.
And it's third along from the green little eye.
See, it says code chips. Everybody find it? Does everybody find that it's empty?
Yeah.
All right. So what we got to do is we're going to put something in there. So now go to the bottom and right click and go to import code chips. Like this. Okay? And then click that. When you do that, a menu should open up. ideally. Hello? Well, it's not opening.
Yeah.
Is it opening for you?
No.
Yeah.
Well, this is a problem.
Can we drop and drag into it?
No. How many people doesn't it open for? Just
everybody on the Mac, maybe.
You know what you do is close your start up Nova again. Just start up Nova again. Has everybody been able to open it and get a menu? Now, choose that file that was called the one that we just created, the one that was called WS1 something.cmp.
Can you go to that second image? So we closed our current working model?
Well, I had to close it, but everybody else doesn't have to.
If you aren't getting that
Yeah.
if you aren't getting that prompt, you have to read.
Yeah, I just closed Nova and opened it up again. And where did I put it? All right, I don't have it. Why isn't it there? All right, so I forgot to pull it out of the thing here. So I'm going to copy it. I forgot to copy it into my area. So I'm going to do that now. And then I'm going to put it in my area. Okay, and now I'm going to do it again. So I click here, import code chips, and so you see the one called WS1 average CMP is the only thing that should be lit. Everybody see that? Or did you choose that? Yes. Now when you choose that, you should have 2 code chips now listed in the code chips listing. Does everybody have that? Okay, so this is the way you import code chips. Has everybody been able to do that? Great. That was the hardest part. Okay, so everybody okay with that? Now these are your code chips. I give them to you with my blessing. All right, the first one, there's 2 of them. There's one called averaging and one called save run. So the one called save run is the one that we're going to do this one at a time. We're going to take the statistics on one thing and then get it to work and then go back and do it on the second thing and get it to work, because it's the same process no matter what. All right? So let's just do one thing. Let's do theta. Okay? Let's start with theta. So one thing that we need is we need a pin to the outside world. And Nick conveniently gave us a bunch of pins that he's not using. If you were using these pins, you would have to add pins to the model. But I'm going to do is I'm going to Shanghai these pins, this pin here called out theta, and I'm going to use it for a new purpose. I'm going to repurpose it. Okay? So we're going to just repurpose it. Are you ever going to need that pin?
They're there for you, Rich.
They're there for me. So that pin, you notice that wasn't connected to anything in the outside, right? So when data was showing up there, nobody was looking at it. Because what we did, we had our graphs pinned here so we could see them up there. So now first thing we're going to do is I'm going to get rid of that arrow because I don't need it. So I'm going to click on out theta and I'm going to go to garbage and I'm going to get rid of it. So we've disconnected it. Now, go to the code chip palette and click the one called save run, like that. And this is just like the other component palette. You now go over here and you click on the canvas and you should get a little orange box that looks like this. And it should be called Save Run 1. Did everybody get that? All right, now,
I think it won't delete. Right.
What?
It doesn't delete.
Your arrow?
Get rid of it, yeah.
Well, it can stay there.
Okay.
It's always you. It's always him. All right. All right, so everybody up to here?
Did you delete it?
Okay.
No, they just never even.
All right, now the only other thing we have to do is we have to hook this saved run into the circuit. I'll tell you what this is doing, all right? What this is doing is each of these variables, unbeknownst to you, you think you are putting new values in each time, right? Every time the clock ticks, a new value shows up there. That's what they are, they're variables. But it's saving all the history. So it remembers every value that was ever in there. Okay? It keeps a history. And we call that history a run.
The save run?
Save run keeps a history. And I can then extract that history and send it out of the model to the top level. And the save run code chip, that's exactly what it's doing.
But anyway, it saved the history. We had the...
Right, but remember we want to do 100, 100, 100, 100, 100. And each time the histories will disappear. And we want to take that whole history and then make comparisons amongst them. Yeah. We want to make cross-cut comparisons. Yeah. So we have to take the whole thing and ship it out. Okay? At least that's how I did it. So here's what we do. Go to right-click on Save Run, right-click, and click Skip Program Code and go to Inputs Outputs. Okay? And this is where we hook it up. So value, both value and, so they both should go to theta. Value, and then click up here to init count and select theta for both of those. So value and init count, select theta. For output, we're going to go to that pin. We're going to go to the pin called out theta. And now if you click this, you should see the right, the stuff showing up here, all right?
Can you
do it again?
Do it again? So for value and for init count, use theta.
For both of them?
For both of them, yes. For both of them. And for run, use out theta. So you should have two wires going into this thing from theta and one going to out theta. Now save. All right, is everybody up to this? Everybody ready? Yeah. Yeah. Problem?
The output pin is connected to two different sources.
You mean this is coming to two different, this is, two things are coming into here?
Two things are coming into the output out favor.
No, there should only be one thing coming in there. Didn't you get rid of the arrow?
No. Yeah, if you didn't get rid of the arrow, then...
It won't be a problem. Don't worry about it. Okay, because we're going to go visit that thing, and right now we're going to change it. Okay? So the next step is to go in, right-click on out theta, and select save run 1.run instead of theta. So we're changing what this thing is outputting. So that all I've done is I've repurposed the pin. And right-click on the pin. Out theta, it's called.
And you have to put
We're just repurposing that one.
Instead of
Yeah, there's only one.
Rich, is there any reason in particular we're creating a new pin?
No. But we might as well because what happens when you create a new pin is you might, it's better not to create a new pin if you can avoid it.
Right now.
Right now. It'll just make things more complicated. You could absolutely add a new pin. But I asked Nick if he was using these pins, and he said no. So.
And we've run into some issues in the past where adding new pins causes errors.
We're trying to make this as clean as possible. But yes, in general, you just have to make sure that the connections are correct when you go back up again. The problem mainly happens is if you add input pins, sometimes the output pins get messed up if they're connected because the numbering changes. So I just wanted to avoid that. But yes, in general, adding new pins is not a problem. Okay, so if everybody it's very important that this pin take this value, otherwise it's not going to work. Are we together? All right. Pardon?
Out theta. Why are we entering in both the things, the theta?
We're only really interested in this connection and going from here to here and then from here to here.
But why twice?
Why is twice?
The input.
Why the input twice? One of them is an initial value. The initial value might come from somewhere else. So it turns out we've separated them in this thing, and I'm taking my initial value from theta as well. In one of my earlier models, I took the initial value from somewhere else. Actually, I could probably simplify this and only have one input. So anyway. So what we've done is we've basically rerouted. Before we were going from here to here, and now we've just rerouted it through this thing. Right? It's a very simple idea. If you pulled something out of here, you plug it into here. You pull something out of here, you plug it into here. Right? Okay, so that's the first half is done. Save, and now go back to the top of the model. Okay? So go back to the top of the model, and now we're going to take the other one of these. So click on the one called averaging. Okay? And now select that and then put one of those on the canvas as well. So you'll notice that averaging is much simpler. It has one input pin and it has 4 output pins. And I'll tell you exactly what they are. The input pin is going to accept the data that we prepared to ship off. And the output pins outputs mean, standard deviation, mean plus standard deviation, mean minus standard deviation. So this is a very rich code chip that does all the computation for you. It's all contained in there. I will just very briefly show you the contents of this so you can get an idea. So if you want to see the contents, go to program code, and this is it. So this is a whole bunch of mumbo jumbo that I'm the only one in the world that understands. And this is doing the job. Now I would say after you look at this, click cancel, because you want to make sure you don't change it. Okay? Again, as I said, anybody who wants to understand how that works, I'm happy to explain it. But all we really have to do now is we have to connect the pins. So remember, we repurposed that top pin, the one called out theta, to deliver the data that we want. And what we're going to do now is just click on this, go to inputs, outputs, and for the input run, there's only one input, we're going to take that data. So that data was coming out of SRW, and it was called out theta, and that's it.
What would happen if we took SRW out X?
It would blow up, because that's not it's not delivering the right thing yet. You have to prepare it by So basically what we're doing is we're putting something in the inside and we're putting something on the outside. Right? Think of it as like a couple of adapters. We're putting one adapter on the inside, one adapter on the outside. Is it funny? Why is it funny?
I don't know.
What was funny? Oh, the blowing up part? With Wayne, it always blows up, so.
I'm an expert at making Nova blow up.
All right.
Can I try to add something to Wayne's question? So when I hear Wayne ask what would happen if I took another pin and plugged it in to this thing, and Rich said it'd blow up, so that's like a metaphor. Like what if I take my European outlet and I plug my port?
Yeah, that's right. So suppose I brought my old, American toaster over here and I plugged it into a European outlet, and I can watch the toaster blow up, right? It's not adapted. You have to connect things that are prepared to connect.
But you connect it at the lower level?
What we did, we changed what was coming out of the lower level.
Yeah, connect the averaging at the lower level.
Yes, you could, but then you'd have to take, you could connect the average in the lower level, but then you'd have to create pins for each of these to come out, to graph it. You have to run a clock chip. You have to run a clock chip to make this work. The key is that the lower chip is now a clock chip. So they're running on different time scales. And that's why you have one thing on the bottom and one thing on the top. So you're running a whole run. The whole run's being delivered to the thing on top. The thing on top takes that whole run as one time unit of data and then uses it. So it's very carefully calibrated to be delivered. So it's like you're delivering a whole, instead of delivering it one at a time, you're delivering a whole bag, and then the thing on top is processing the whole bag as one step. So it's a definite, that I tried to do it on one level, it didn't work. Okay, it doesn't work. So you have to do it like this.
I mean, that's a very insightful question, because it helps you understand how things work at the different levels.
Okay,
in relation to what Wayne asked, what's averaging the code chip, averaging 1, what it receives now is a vector of numbers, right?
It receives actually, yes, a vector, receives a vector of ordered pairs, effectively, yeah. Because it has the x values as well.
Okay.
Yeah.
And if you would have connected out x, it would have received a scalar.
That's right. It's expecting this vector. Well, it's not only expecting a vector, it's expecting a data structure. Because it's accessing that data structure according to the rules of the data structure. So that data structure is a vector data structure. And so if you look at the code in that code chip, there's all kinds of references to methods that data structure understands. Okay?
So the visual metaphor is not consistent, right? Because we have output pins and input pins, right? Something comes in, something goes out. Yet, the fact of the matter is that top pin is spitting something out that's different from what all the other pins are spitting out. And visually, we don't have a way to reconcile that. So the only way right now that you have to think about that is just to know that one of the pins is giving you a sequence and the other is giving you...
Yeah, someday we make that pin be fat.
So
to show that it's spewing out vector data. Sometimes it spews out matrix data, right? I mean, it depends on the situation. But the beauty of this is that these conduits can handle all kinds of data, and you just have to make sure that you have the appropriate adapters, and all this, ultimately will be explained so that it becomes part of the vernacular for using Nova. It's not that hard once you sort of understand what's going on. Okay?
And this is part of Nova that's probably more under development than other pieces of Nova. A lot of the other visual metaphors are very consistent. We can differentiate a flow that is a sequence versus a flow that is a differential equation. And you can see that in your visuals. Like we saw those green stocks, they're different than purple stocks. Those are actually different ways of managing data, managing information. And here's a place where we have an early implementation of this kind of connectivity, where it's functional. And Rich pointed out functional and powerful, but the visual metaphor isn't quite there yet. And the visual metaphor could be improved so that you could understand, well, what I'm passing out here is one data type, and I need to input that as a data type on the receiving end as well. It's different.
Yeah, the internals will make it happen. Okay, we got one more thing to do. Yes.
The outputs of the chip you didn't.
Now we're ready to hook up the outputs. We're going to do something about them, because what we want to do is we want to graph them.
No, but when you on the properties of the chip, you didn't touch the.
No, I didn't touch the outputs because when I'm working with a graph, I like to let the graph take those things as inputs instead of, right? There's two ways you can connect things. You can say this is outputting to this, to A's outputting to B, or B's inputting from A. Right. So with a graph, I'd rather do B's inputting from A, because that way I can control the order that they're in. Okay, so my tendency is not to set outputs if those outputs are just going to a graph. Outputs can go to more than one place. They can go to multiple places, but they're only going to a graph now. So I'm going to do it from the graph instead.
You change only the input.
Right. All right. So we could run this now. This is runnable. The only thing is we've got this data coming out of here and it's not going anywhere. We're not looking at it. If you want to run your model now, let's just run it a couple of times to make sure we're in good shape. So I'll do capture. Well, first I'm going to do save. Now I'm going to do capture, load, init, and then I'm going to do step. And you'll notice we just have everything we had before. Everything as it was before should still work. Nothing has changed. That's a good sign, right? But meanwhile, there's nice little numbers in these pins that are sitting there saying, look at me. All right, so let's satisfy that by providing a view on those. And that's the graph that we want to create. So we're running out of real estate. I thought I would, way I'm going to handle this, so now we can close the code chip palette. And I'm going to now open up the components palette. That's the one we've been working with all along. I'm going to select the graph. This should be old hat for you. And I'm going to put the graph right here next to averaging like this, and I'm going to call this theta stats, just like that, say. Doesn't matter what you call it. And of course this graph is going to sit right on top of another graph over here. So what I'm going to do is I'm going to move it over so that it has room. There's really a real estate problem here. So I'm just going to pull this thing over here to make space. And now we're ready to do something with it. So I'm going to now, this is all stuff you've done before. I'm going to take the mean plus standard deviation, and mean minus standard deviation, and I'm going to graph them. And I'm going to actually select a uniform. Have you done this before? I don't think we've done this before. We're going to select a uniform scale for these. So I think I saw a range of minus 50 to 50 as being reasonable. So I'm going to select all three of these. You do that by pressing the shift key. Okay, see that? And then go over here to scale and click self. And then go to low and make it minus 50. And go to high and make it 50. Okay, and then the last thing you have to do is click set. If you don't click set, it won't work. Okay, does everybody see what I just did? I selected all three of these. I clicked this to self. I set low to minus 50, high to 50, and I click set. Now that'll create a single scale for all three. As you can see, we have a single scale there going from minus 50 to 50. And now we should be in good shape, because if I do capture, load, init, and I'm going to just use step, okay? So there's my average. Now, of course, I'm averaging one thing. When you average one thing, it should just be a duplicate of the thing itself, and that is what it is, just on different scale in the matrix, in the graph rather. But now I'm going to do the second one, and now all of a sudden I've got some deviation. And as I run these, notice how this does this very neat kind of smoothing out. I'm just stepping. I could hit run, and I could let it run by itself. So everybody should have this working this way. How are we doing? Are we all in business?
Yeah, but what are your parameters set for? Because mine is giving a bit of a different picture.
Well, I set,
Your theta may be different, or your B may be different.
Maybe your B is different.
That's why I'm asking.
Well, my parameters are set for A of 0.78 and a B of 0.1.
But your theta hat may be different.
My theta hat is 0.
Yeah.
That's your initial theta. If you set that to 0.
That's why the angle is close to 0, is because the theta is...
Okay, so how many people got this to work? How many people got this to work?
No, if theta hat is 90, then this thing will be up to 90. Because it's heading in the direction of 90.
But A should matter. Only A affects the choice of angle.
So you're all now code chip users. You've transplanted the code chip. You've soldered it into the circuit, and now you're getting the benefits of that.
Yeah, but it affects it in the direction, or in a particular direction of theta hat.
We're looking at theta.
Oh, we're looking at theta. Yeah, but so theta will tell you what direction you are.
But theta hat
I can't hear. Yes. They're cross-sectional statistics.
It's not over the first 100.
Well, it's 100. You're looking at, pick a time, 25. You're looking at the variation at each. So at point 25 here, you're looking at the variation across the point 25 in each of the runs. We did 100 runs, right? So at point 25, theta was this, theta was that, theta was this, theta was that. That's what we're looking at. And each one of these represents the cross-sectional statistics for that.
Over the 100 of that point?
Each run at point 25 is going to have a certain theta, say. So I look at that. And that's what I'm seeing here at 25. At 50, I'm seeing another one. Okay? So you notice why is it very close?
Across runs, across steps.
Across steps, yes. So why is it very close to 0 here? Because it hasn't been, they all start at 0 and there hasn't been a lot of variation. Yeah.
It's kind of awkward to look at the standard deviations of accumulating theta. Is there any way to look at theta only at the range of minus 0 to 2 pi?
Yeah, you've got to reset your theta modulo 2 pi, so we haven't done that.
Yeah, I think what you do is you...
The standard deviation is...
Well, I think what you do is you have to go back down to the model, and then just when you put a new theta value in, always do mod 2 pi.
It's not worth doing because what we should really be looking at is D. So we should go back to the other chip, calculate D, and then feed out the D value.
Well, you're right. We have time to do one more, okay? Let's do the same thing, but for X. You wanted to see X?
Same thing for X.
So let's just do the same thing for X.
Okay.
Has everybody got something that works? Who said no?
And
Where's Nick? Nick will come over and help you.
Who needs help?
Anna, what's her name again? Naama. Yes, that's you, right? Yes, Nick will help you.
Thank you.
Okay. Shall we do one more? You want to do one more? Let's do X. Okay?
Why don't we just calculate D over here by taking the square root and then just take D?
Well, let's do that later. But
I mean, it's just one calculation here and then feed it out.
All right, let's do that. All right, let's do that.
That would work. If we make a D here and take out X and Y.
No, I won't be able to do. I won't. It's not that simple because there's no. This doesn't have a history.
So you'd have to make this a stock.
It can be done, but this is thinking on my feet.
Oh, okay.
Okay, it's not worth it. Yeah.
Okay.
Everything I say is being recorded, so I better watch what I say.
Yeah, X is easier.
We'll do D later. Yeah.
Okay, so A is A and B are the parameters which I'm playing with.
Yes.
So the constant A,
yes,
which is pi, and 0 B equals 0 gives us a random walk.
Okay.
So when I looked at that, when I did it, and it didn't fluctuate a lot.
Well, let's look at it later.
I think this is a great time to break out a conversation, actually. Wayne, let me propose this. I think there are very interesting conversations going on in different parts of the room about how the standard deviation around the mean changes with parameters A and B. And I'm hearing that conversation up here. I think this is also a conversation we had back here. But trying to figure out how the space between how our distribution changes with different values of A and B. And I think we're trying to figure out if A is close to pi, if A equals pi, what do we expect our distribution to look like versus A being some number less than pi or some number approaching 0. And I think I think people have different explanations. Well, I think back here there's the question, well, how come it's not doing what I expect it to do? And my question is, what do you expect it to do? What do you expect your distribution of step sizes to look like as A approaches pi?
Well, what do we want? Do we want to do another? Do you want to do that kind of thing? Now it's 15 minutes to lunch, or do you want to try to do another one of these? Maybe.
Let's think about that, and let's talk about that first thing when we get back from lunch. So let's go ahead and implement one other thing. Let's let Rich finish, and then I think we want to talk about what our results actually mean, because we're generating results, but we're struggling to interpret them. And I think it would be good to have a discussion about the interpretation.
Right. Well, I'm going to show you how you can just follow the same pattern that we just followed and bring another statistic into play. Okay? So here's what we do. Ready? So make sure you've saved everything first. Do a save. Yeah.
If you calculate your D in a command module over here, would that do it?
You need it. It has to be in a stock.
So the command module wouldn't give you.
What you can do is you can set up another stock and take values of X and Y, put that into the flow. Should we do that now?
Yeah, let's do that because that's the only thing.
All right, Wayne is actually asking us to try something a little more elaborate, so we're on a bit of untested ground here, but what the hell? We're going to add a new stock.
Two sequences, two
All right?
sequences of 100 tests. And then just want to take the mean.
We're going to add another stock. And I'm opening components here, so
And what you see is that over time, you actually
we'll call it D. So enter stock name D. We're going to make the stock purple
and it smooths out.
by making it discrete. And now for any time you have a stock, you have to have a flow.
You're actually approaching
And so we'll just call this decalc, like that. Okay, now drag the cloud, and now you want to put arrows from X and Y to D.
Yeah, so that's a great question.
Make it biflow. So drag arrows from X and Y.
It could be in flow.
It won't matter because it's always going to be positive anyway. Yeah. It's, in this case, it's not going to matter, but make it biflow, just out of habit. Now I'm opening decalc. I'm making it biflow. And now I'm going to take math.square root of x times x plus y times y.
Richard, they're asking to go slower.
All right. Well, I'll leave this on the board for a second.
Okay, so this says math dot square root open parentheses x times x, y times y. Make sure that you've connected. Well, you don't have to connect the arrows.
Yeah, I have put them in though.
Yeah, yeah. So you've got this new stock called D, and we're calculating it. So every time you calculate x and y, we now calculate the square root of x squared plus y squared.
Yeah. Now D is going to be one time unit behind, so we're going to be off by one, but that's all right.
That's okay.
Yeah. All right. So we could run this and look at. I think we ought to make sure that D works.
Yeah.
I don't like doing this without checking it out. The easiest way to check something out quickly is to make a table and look at the numbers. So I'm going to click here to make a table over here. The table's name is D. Okay, in fact, I'm going to put X, Y, and D in there. I'm going to put all three so that I can see the numbers. So I'm going to take X, Y, and D. I'm going to table all three. Okay? So there's our table. And now let's just do a capture here and see if this works. I'm going to do a capture load exec. Well, first I'm going to save. I always save. Capture load exec. And what have I got? So I've got X, Y, and D. And it looks good to me. I mean, I haven't worked it all out, but
Connect the table to the flow or to D?
Yeah.
I'm sorry?
You don't have to, you just open the table up and you see what variables you want. You don't have to do any connection.
Okay, so the numbers in D are one step behind. If you look carefully here, you get 0, 0, and then this number here is really this one plus this one, you know. But it doesn't matter, it's still a sequence of distances. So the timing is a little off, but the reason why we wanted this is because this is a much more interesting thing to get statistics on than X or Y. So I'm going to leave the table there. What the, just leave it there. Doesn't hurt anybody. I won't pin it because I really don't want to look at it. And now what I'm going to do is I'm going to do to D what we did to theta. Only we're going to need a new output pin. So I'm going to add an output pin. A new output pin, we're going to call it out D. Okay? So there's our new output pin. Everybody good with that? Everybody on the same page?
Can you repeat what you put inside the flow?
Inside the flow is just 0 to start with. Oh, in the flow, I'm sorry. Here's what's in the flow.
You can't see it from here.
It's math dot square root, capital M, A-T,
Let me write it.
dot square root, open parentheses, x times x plus y times y.
Here, I'll make it big for a second.
X squared plus y.
Can you see it now? It's like an eye chart here.
Wait.
No?
Can we see what the name is?
Okay.
Yeah, so these one constant behind.
Can I go on?
Yes, that's one goes zero there.
Are you good?
Yes, square root, square root, square root, If you've got that expression.
All right, are we good? Are we good? Going once, going twice, okay?
Okay.
Okay. All right. All right, so now we're going to, does everybody see that I added this? I added this pin down here. Okay, I'll make it blow that up too. There's the pin. Out D. I haven't put anything in it yet. Just put it there. Are we okay? All right. So.
Hey Rich, did you pin your table to the top or?
No, I'm not. I could pin the table to the top, but I'm not going to. I just put that table in to make sure that D was functioning.
Yeah. So
Okay.
the table is just to serve to, yeah.
It was just to serve to test it. I could delete it now, but I kind of like it. All right, so now we have to do the code chipping. So open the code chip palette again. All right, open the code chip palette again. And remember, which of the code chips do we put on this level? Save run. So just do the same thing. Click save run. And then click on the canvas.
Question?
And now what we're going to do is we're just going to hook this up the same way. That is, we're going to take, for inputs, we're going to take D as both value and initial count. Take them both. Okay? And for output, we're going to go to out D. All right, everybody good with that? And then you have to go into out D and you have to program it by clicking on this save run 2 dot run. Notice this one's called save run 2. Every time you add a code chip, the counter increments so that the code chips are not they all have slightly different names. Everything has to have a slightly different name. Okay? And it manages that for you. The code is the same, but it's a different instance. All right. So now we've got this programmed. Click save. And now when we go back on top, we should see that there is one more output pin at the very bottom there. Everything else should be okay. We'll check it out when we go inside there, but everything else should be okay. So what do we have to do now? Anyone remember? What do we do now? Right, we have to get the averaging code chip. So we click here and stick it here. So that one's called averaging 2. I'm just going to move this stuff over a little bit to get some room. Whoops, I got one too many. All right. And now I'm ready to hook this up. So we right click on this program code, okay. I'm sorry, input output. And we are going to take, as our run, we're going to take srw.dout, or out D, I guess it is. And we're not going to do anything on the other side. So we're just going to do this. Now I'm going to be, because I'm a careful person, I'm going to open up this chip and just check the inputs and outputs to make sure that they're still correct. All right, so there's A goes to A batch. The hat goes to the hat, theta hat I mean. B goes to B. That's it. And that the outputs are also correct. So out theta goes there, and then nothing, 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 nothing there. So everything looks good here. This looks good. If it worked for me, it should work for you. Okay, but we're careful to make sure, since we added that pin. So there's our new pin. It's really more, problems happen more when you remove pins than when you add pins. But someday, you know. All right, and now what is the last thing we have to do? We have to create a graph for this. So we have to go over here to create the graph. I'm running out of room for these things, but hit the graph button. Okay. And what happened? Let me make sure I'm going to do a save first. I'm going to hit the graph button, which is this. And I'm going to go, let's call this D-stats. And now I'm going to hook this thing up. So I open it up, and what I want to do is I want to take averaging to mean, averaging to plus standard deviation, averaging to minus standard deviation. And do you have any idea what a range might be for this? We could look at those numbers we saw. So they're only positives, right? Because they're distances. So let's go to 0 to 1,000, maybe?
Square.
So let's try something. I don't know if this is correct, but let's scale this from 0 to 1,000. We may find that that's way off.
At the beginning, you can just let it do automatically, and then.
Yeah, we could do that and see what it gets. So, all right, you want to do that instead? Fine. So forget it. All right. So now we'll have 3 different scales there, but it won't look as good because you want to get that thing where it's around them. So, but on the first run, let's just see what kind of range we get, and then we'll scale it. So this is the moment of truth. Okay. This is it. Is it going to work? I don't know. Let's hope so. I'm always very sheepish about this the first time I hit step instead of run. And looks like we got something interesting. So there we go. It looks like we're getting some interesting results. So if I run this, there we go. And the numbers are actually a lot smaller than I thought. Because we got square roots, you're right. So it looks like they got somewhere from 0 to 10 is the biggest number I'm seeing there.
Maybe just put it on automatic.
Well, I did, but now that I see what I'm getting, I'm going to, because I want to see the mean with the two, put it into the tunnel. So it looks like it's 0. It looks like 10 is good enough. Let me make it 20. Or let's make it, I mean, you guys, you can decide how you want to do this.
Why do you have the standard deviation on both sides of the mean?
Because that's what Wayne wanted.
It's just common practice, but very often standard.
I mean, you have the green line crossing.
Because it's a different scale.
Okay.
That's why I wanted it on one scale. So we did it the first time to find out what order of magnitude we're in. And now we'll do it again.
So if the distribution is not symmetric, sometimes you plot minus the standard deviation and you get negative.
There we go.
Negative,
so this is very, very cool. Very, very cool.
What is the top one and what is the bottom?
The top one is theta, the bottom one is d.
Oh, okay. Yeah, so when A is, when you got a simple random walk, that blue curve should look like a square root curve.
Right.
And then when you've got a highly directed random walk, that blue curve should look more linear.
So
You're talking about square displacement, and here we're talking about displacement.
Now, mean squared displacement.
But in this case, is D distance right now?
Yes.
D is distance.
Oh, so the square, we got the square root of the displacement. Yes. So the displacement should be like the square, should look like the square root of time. So if you're plotting displacement there, it should have, with time, the displacement should look like a square root function. So it should be like to the power of half, as a function of time.
So it's not the square displacement that should look like the square root.
Well,
I thought it was the square displacement actually.
No, displacement increases like the square root of time. So it's scaled to the square root of time. So that means as So if you want a double displacement, you have to go
4 tons.
4 tons. Yeah.
Okay, how many people succeeded with this?
I think I hooked it up incorrectly.
You have a problem?
It works, but it's not showing the same number.
Did you come up with a single scale? How many people have this working? It's not working? Oh, you got it working. You didn't hook it up right.
That's one of the nice things. Never you.
Okay, that one, I think he didn't hook things up right, the kind of error message he's getting.
Yeah.
I did it before.
Ron, did you get it to work?
I am trying to do it on yesterday's.
Okay.
On my.
Did you get it to work?
Not exactly, because I just lost somewhere in the middle.
I'm getting a. Getting an error.
This is.
Null.
Yeah, which is not very descriptive. Right?
What does it say? You're getting a null error?
There's a null someplace. Please check your equation.
Are you sure you hooked everything up the right way?
Well, I did get displacement.
Yay?
I think we're done.